Hello, everybody. Welcome back. Today we're going to be looking at Unit 5.3, which is called Concentrations over Time. It's a slightly different way to determine a rate law than what we saw in the last subunit. I would ask you to have your formula sheet provided by the College Board. Have that out because that's going to be very useful for us today. So let's get started. So to start off with, let's just refresh our memories on what the word order even means. In the last subunit, we looked at how to determine what was called a differentiated rate law. And we were able to determine the order. An order in a rate law shows up as an exponent. So for example, what you can see in front of us is a differentiated rate law. Rate equals the rate constant times the concentration of A, and I can see that it's raised to the first power. That means this is a first order differentiated rate law. Please don't let this part in the middle here throw you off. This is a way of just once again reminding you how rates are calculated. It's a change in concentration of some part of a reaction, usually a reactant, over a change in time. The only reason that negative is there is because reactants are being consumed over time. They're going away. If this rate was described with a product, that negative wouldn't be there because products are created. What we're going to look at today is moving beyond what are called differentiated rate laws and looking at what are called integrated rate law. An integrated first order rate law looks like this. Now, let me show you on your equation sheet, your formula sheet. There is a section with the title Kinetics. And there are 4 equations in this section that are going to be very helpful for us today. The good news here is that there is very little memorization. The hard part is knowing how to interpret these formulas that you are given. And I want you to notice something. This integrated first order rate law that I have written on the screen there looks slightly different from the one that is written on your formula sheet. If you're looking at your formula sheet, this is the same formula as the second formula in that kinetics section. Now, it does look slightly different. So let me just show you what I mean. On your formula sheet, it looks like this, minus, and we're going to talk out what everything here represents. What are all these variables? Okay, it looks like that. So just to be clear, these ln's, that's natural log. Okay, make sure that you know where that button is on your calculator. It's not log base 10. This is natural log. And the brackets, of course, mean molarities, concentrations. Where you have this little sub-zero, that means the initial molarity of that reactant. And where you have the subscript T, that means the molarity of reactant A after some time T has gone by. And that's what that T is right there, is time. And the lowercase k, of course, is the rate constant. Now, you might say, why, Ms. Giordano, why do you have it written the way you do on your screen versus the way that it's written on the formula sheet? And I'm going to tell you why. First of all, I want you guys to notice that the way that I have it written in sort of orange color is just a rearranging of the way that it is written on the formula sheet. And I'm going to show you on the next slide why I have it rearranged like that. Many of the problems that you all will be presented with in this section are going to include graphs. Okay, I'm just showing you that integrated rate law again. And the reason that I like to rearrange it like that is so that it lines up nicer with a linear regression line. Back from algebra, you learned this. Y equals mx plus b. And here's the thing. Many of the problems you all will be presented with are going to give you a graph already plotted for you. You won't have to create the graph yourself. And I want you to notice what's on the axes of this graph and how nicely it lines up with this y equals mx plus b. What is on the x-axis of this graph is time. Okay? Could be in seconds, could be in minutes, hours, whatever, but it's time. What is on the y-axis? Natural log of the molarity. And the thing I want you guys to notice in this graph is that this plot is linear. It's straight. When you're presented with a graph like this and you say to yourself, okay, what's on the axes? Time is on the x, natural log of molarity is on the y, and yes, it's linear. That is proof that this data is first order. So if a plot of natural log of concentration versus time is a straight line, then you can definitively say, yes, this data, this reaction is first order. And we're going to talk about in just a minute, well, what happens if it's not straight? What does that mean? What if it's not linear? But again, guys, the reason that I like to rearrange my integrated rate laws differently than the way they're presented on the formula sheet is it makes it easier to see these relationships. Not just what's on the x and the y-axis, but what is slope? If you can find the slope of that line on the graph in front of us, again, think back to algebra, pick 2 points, change in y over change in x, that is equal to the negative rate constant. Finding the slope is a way for you to find the value for the rate constant. The y-intercept is equal to the natural log of the initial molarity. That would be something else that you could be asked to solve for. So I always ask my students to, just to the right of each formula on the equation sheet, to rewrite each one of these formulas rearranged. That's totally up to you. I just think it makes it a lot easier to see these relationships. Something else you're going to be asked, you might be asked about in terms of a first order reaction is the concept of half-life. And you've likely heard that term before. Let's just refresh our memory on the definition. Half-life, first of all, guys, is a length of time. That could be in seconds, minutes, years, decades, whatever. It's the time required for a reactant to reach half of its original concentration. And again, look at your formula sheet. You have this equation that's on the screen in front of you. You have it. That is the formula for half-life of a first order reaction. That T1 half is the half-life and K is the rate constant. Let me just be clear about this. This equation on the screen in front of you that is on your formula sheet is only to be used if the data is first order. If it's anything else, not first order, you can't use that formula. Okay. And I want you to notice that in this formula, nowhere do we see concentration. The half-life, and this is something unique to first order data only, the half-life, the length of the half-life is not dependent upon concentration. That's unique to first order. One final thing about this, a little fun fact, all radioactive decay, like alpha decay, beta decay, all radioactive decay follows first order kinetics. That's just a little fun fact. So let's look at a sample problem. It says the radioactivity of a sample of iodine-131 was measured. The data collected are plotted on the graph below. And then we're asked some questions. If you would like to pause the video here and try to answer them on your own, go right ahead. Otherwise, I'm going to talk through them. The first question, part C, we're starting with C, says, determine the half-life of iodine-131 using the graph. And again, what is the definitive half-life? It's the length of time it takes for that initial amount to be cut in half. So I can see on the graph that we are starting up here with a value of 16,000 decays per minute. Don't worry about if that unit is confusing you, just think that is sort of the initial amount. What is half of 16,000? That would be 8,000. And how long did it take for us to get down to 8,000? That took 8 days. Okay, so that is the length of the half-life. Make sure you pay attention to the units of time on the x-axis. This one has used days. Sometimes they use seconds, minutes. Just make sure you pay attention to that. All right, the next part says, the data can be used to show that the decay of iodine-131 is a first-order reaction. So we don't have to determine that. They're telling us, as indicated on the graph below. Label the vertical axis of the graph, okay? Remember, using your formula sheet, we have that integrated rate law. We know that when something is first order, the linear graph should come when time is on the x, and I can see that it is. And what is it that's on the y-axis? It should be the natural log of the molarity. Okay, so that's what should be on the y-axis. What are the units for the rate constant? That goes back to unit 5.2, subunit. If you need to go back and watch that video again on how to determine the units for the rate constant, you should do that. But if the data is first order, the units for K will always be the same, inverse time. In this case, time is being measured in days. So days raised to the negative first power. And then the last part says explain how the half-life of iodine-131 can be calculated using the slope of the line plotted on this graph. And again, guys, if you will think back to what that integrated rate law looks like for a first order reaction. I'm just rewriting it out. And they've given us a little bit of a hint saying using the slope, well, what's the slope? What's in that position of m in y equals mx plus b? It's negative k. So the slope is equal to negative k, and then if I know what the slope is, I can solve for k, then I can plug k into that half-life equation, and I could solve for it. Please notice it doesn't actually ask me to solve for it, it just says, how would you solve for it? So you'll have questions involving the integrated rate law and the concept of half-life, but here's the thing. What if that plot of natural log of molarity versus time, what if it isn't straight? Well, then it's not first order. So what could it be? It might be second order. Again, what does order mean? Order means that in a differentiated rate law, we would see an exponent. And in this case, since it's second order, that exponent is a 2. What does the integrated rate law look like for second order data? It looks like that. Don't memorize it. Let me go over to my formula sheet. Here it is. Okay, so here was the first order formula integrated rate law. Here is the second order integrated rate law, and I bet you can guess that I'm going to rearrange it, and I did. If you look at how this is written on the screen versus how it's written on your formula sheet, you can see that I have rearranged it. Why have I rearranged it? So that it lines up better with that y equals mx plus b format. So before I pull up a graph of what this should look like, think about what should be on the x-axis. What's lining up with x? Well, that would be time. What's lining up with y is not the natural log of molarity, but 1 over molarity. And so guys, what you might be presented with is graphs like this. Again, let me say, you are typically not going to be asked to plot these yourself. They will be given to you, and you have to interpret them. Look at the one on the left. Time on the x, natural log of concentration on the y. And I can see it's not straight. That tells me this data is not first order. So let's look at the graph on the right. Time on the x, 1 over concentration on the y, and I can see, yep, it is linear. So if a plot of 1 over molarity versus time is straight, this data must be second order. Okay? And again, you could be asked to solve for the rate constant, and how would you do that? Look at that, how y equals mx plus b lines up. The slope is equal to the rate constant. Now, let me preface this slide by saying that it would be pretty unusual for you to be asked to solve for the length of the half-life for second order data. For whatever reason, the AP exam doesn't typically do that, but they do on occasion. So I'm just going to show you this formula, okay? Now, first of all, is it on the formula sheet? No, it isn't, but that's okay. I'm going to show you how you don't need to memorize it, okay? But T1/2 is the length of the half-life, K is our rate constant, and A sub 0 is the initial concentration. Please remember, the first order half-life reaction, or formula, excuse me, did not have any molarity in it. This one does. Okay, now, do you need to memorize this formula? Absolutely not. Okay, let me show you guys. If you look at, this is second order, so I'm going to just rewrite the integrated rate law for second order data. Okay, no need to memorize that, it's on the formula sheet. If you were ever asked for the half-life of a second order situation, pretty unlikely, but could it happen? First of all, guys, you would have to be given the rate constant value. You would have to be given that, okay? This would be your unknown, okay? Remember, half-life is a length of time. You would also have to be given the initial concentration, because second order half-lives are dependent upon the initial concentration. So guess what? Let's make up a number. Let's say you're given the K value and you're given an initial molarity of 2 molar. Okay, you'd have to be given that. Well, if it's a half-life, what is that? The length of time it takes for that initial value to be cut in half. What's half of 2.00 molar? That would be 1.00 molar. You can cut that number in half and plug it in, and then solve for T, which would be the half-life. But again, do I think this is really going to come up on the AP exam? To be quite honest, probably not. But there it is. Okay. Now, what if both of those graphs on the previous slide were not straight? Well, it's not. That would mean it's not first order data, it's not second order. The third and final option, ladies and gentlemen, is it could be zero order, okay? Now you might say, why didn't you just go in order? Why didn't you present zero order first, then first order, then second? Zero is probably the one that shows up the least often, so that's the reason why I presented it last. But again, order means exponent. Look at our differentiated rate law, guys. K times the molarity of A raised to the 0 power, which anything raised to the 0 power is just 1. So a differentiated rate law for zero order data can just be written as rate equals K. You can, of course, write it like that if you prefer, your choice. Okay. But that's the differentiated rate law. Here's the integrated rate law for zero order data. Don't memorize, it is on your formula sheet, although again, I have rearranged it. You can guess if you line this up with a y equals mx plus b situation, you can guess what the graph is going to look like. Time is going to be on the x-axis, and regular plain old molarity, no natural logs, no 1 over, that's what's going to be on the y-axis. And if that plot is straight, then you can say to yourself, ah, okay, this is zero order data. Okay. Now, again, would you be asked for the half-life of zero order data? Probably not, because like second order, it is also dependent upon concentration. No need to memorize a formula though, ladies and gentlemen. You would have to be given this, you'd have to be given that, and whatever that initial value is, cut it in half and plug it in there. That would allow you to solve for the half-life. But again, you'd have to be given K and you'd have to be given that initial concentration to solve the problem. But unlikely to show up. This chart in front of you, guys, is money, okay? It summarizes everything we've just talked about, right? In problems like this, where you're going to be presented with graphs, you really only will have 3 options. The data could be 0, first, or second. Orders higher than that are above the reach of AP Chemistry. But in this chart, you've got the differentiated rate laws, the integrated rate laws, plot needed to give a straight line, the half-life formulas, the relationship to slope, and using slope to help you determine K. Guys, don't memorize this, okay? This line right here, those are on your formula sheet. Okay, so is this one, but anyway. If you can simply remember that these integrated rate laws can be rearranged to be lined up with a linear regression line, you don't have to memorize anything. You can see what's going to be on the x-axis, what's going to be on the y-axis. How does slope relate to the rate constant? You don't have to memorize anything, and that is awesome. So what does a problem with this sort of information, what does it look like? Well, guys, it might look like this. As I said, probably not going to have to create your own graphs. They will be created for you, and they're going to look like this. So we're given a reaction, we're given some graphs, and we are told to determine the order of this reactant and explain our reasoning. Determine the rate law. That means, guys, when you just see the phrase the rate law, that means the differentiated rate law. We are to come up with the integrated rate law, and using the graphs only, we need to determine a rate constant value with appropriate units. So if you would like to try this question on your own, pause the video right now. All right, let's talk through this. Our first order of business, no pun intended, is to determine the order and explain our reasoning. And if you look at these graphs, all of them have time on the x-axis, but as you look from left to right, the first graph on the left, we've got plain old molarity, and I can see that graph is not linear. That tells me this data is not zero order. So we move to the middle graph. Natural log of molarity on the y, also not linear. That tells me this is not first order data. If we look at the graph on the right, 1 over molarity, it is straight, it is linear. So I said that C4H6 is second order, and guys, you have to explain your reasoning because the graph of 1 over molarity versus time is linear. Please avoid words like straight or simply saying the graph on the right. You need to be very specific which plot is showing a linear relationship. Okay, so now that we know that it is second order, determine the rate law and the integrated rate law. Okay, the rate law is just my differentiated rate law, that's the one on the left. And my integrated, I didn't have to memorize any of that, that came straight off of the formula sheet. Last part, determine the rate constant. Well, keep in mind that where slope lines up in my integrated rate law, that is the value of k. So all I have to do is use that graph on the right to find the slope. I pick 2 points. You can pick any 2 points you want. Change in y over change in x. And I got a value right around 13. Okay. Now, if you chose 2 different points, and also keep in mind we are estimating values off of this graph, you can probably see I chose this value, this point, and this point. I was estimating a little bit, so usually the AP graders will accept sort of a range of answers. So I got right around 13, and you can see that I have my appropriate units for something that is second order. So let's look at what might a multiple choice question look like. So we have a reaction, and then it says the rate constant for the decay of the radioactive isotope X, according to the equation above, is blah, 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 days to the -1 power. The slope of which of the following graphs is correct for this decay and could be used to confirm the value of K. So you're not actually having to calculate anything, but you do have to pick out which graph is appropriate. Now you might say, how can I answer this? They haven't told me if it's zero order, first order, second. There are hints, and here is one of them. You might recall that I told you that all radioactive decay is first order. Okay, now you might say, oh my gosh, how am I ever going to remember a random fact like that? Well, even if you don't remember that, there's still a way to figure it out. Look right here. Look at the units for the rate constant, for K. It's inverse time. There's only one type of data that has units like that, and that is first order data. Now that you would be expected to either remember or figure out. And now that we know that it's first order, you can look at your formula sheet and say, ah, there is my integrated rate law. I know what should be on the x. I know what should be on the y. It's natural log. So there's your answer. Okay. Let's look at one more practice problem, and I just want to explain something that I sort of hinted at but didn't really explicitly go over. It says the ammonium salt of isocyanic acid is a product of the decomposition of urea represented below. And there's our reaction. A student studying the decomposition reaction runs the reaction at 90 degrees. The student collects data on the concentration of urea as a function of time, as shown by the data table and the graph. The student proposes that the rate law is rate equals K, and then we're shown the molarity of urea, and look at the exponent. There's nothing there, which indicates that the student is proposing that this is first order. Explain how the data supports the student's proposed rate law. Well, guys, if you remember what I said about half-life, first order data is the only type where the half-life is not dependent upon concentration. So what does that mean? Okay, well, I want you guys to look at something here. Look at the initial concentration of urea. It's 0.1 molar. What's half of 0.1 molar? Well, that's 0.05 molar. And how long did it take for that to happen? It took 10 hours for that initial amount to be cut in half. Well, what if another 10 hours goes by? Was this amount right there, was that cut in half? Yes, it was. What if another 10 hours goes by? Was it cut in half again? Yes, it was. We're seeing a consistent half-life of 10 hours. You can see it on the graph as well, that every 10 hours the amount is cut in half. And guys, that is something unique to first order data. The data in both the data table and the graph show a constant half-life of 10 hours, which indicates first order data. You would not see that in 0 or second order because the amounts change the half-life when it's 0 or second order. Okay. So now that we know the half-life, look at the last question here. It says, using the proposed rate law, which we now know the student's proposed rate law is correct, determine the value of K. Well, if I know that the half-life is 10 hours, I can plug it into that half-life equation, solve for K, and I've put in my appropriate units. So that's something else, another type of free response question that you could see. So, that was a lot. But let me just show you one final thing on this equation sheet. Okay, this kinetics section, not only is everything given to you, but it's in order, which is so great. Like this top one, that's the integrated rate law for 0, then first, then second. Okay, and then at the bottom you have that half-life formula, which again is only to be used if the data is first order. Okay, so I know that was a lot, but I hope you all have learned a little something today, and I look forward to seeing you next time.